Cultural extra credit for today, MathStat341, lecture 30-something, day 30-something. This is the complex analysis day. What movie has this shirt playing a prominent role or in a famous scene? Belushi is is the name of the actor who is wearing the shirt. All right. So today is to give a brief introduction to complex analysis. If necessary, this will continue to Wednesday. This will not be on the test. This is just to give you a sense of what do you need to make this class rigorous. And a lot of this is going to be a function of how much detail you want. And it's going to be a function of how much you remember from your previous classes. I am working under the assumption that that is with an epsilon of 0. If you remember Green's theorem, that's wonderful. That will make my life so much easier, but I am not assuming that you remember Green's theorem. Or you might have taken 150 with somebody other than myself and not actually seen Green's theorem. When I teach 150, I believe you have to cover Green's theorem. As a mathematician, if I don't do this, I fear I will be damned for all eternity. It is a beautiful result. And it turns out it's essentially what goes on in complex analysis. Complex analysis has a lot of strange facts. Essentially, you can convert most integration into algebra. But it's not indefinite integration. It's integrations over nice regions. Now, in the plane, the geometry is very different than on a line. In a line, when you want to approach a point, and I apologize, I threw out my right arm playing tennis with Cam. It finally was beginning to recover until we had the monster snowstorm outside, in which case it's now been destroyed again. When you have a point, how many ways can you essentially approach the point to take a limit?
2.
Essentially 2. You can go like this, and you can go like this. Yeah, yes, you could hop back and forth, but it's really essentially just those 2 limits. In the plane, you have an infinitude of paths. You could have the nice spiraling in. You could have some kind of strange thing like this. And when I teach 150, or at least when I used to teach 150 and my kids were younger, I had all the kids in preschool make scribbles like this and give them to all of my students as, this is your personalized image of what multivariable calculus is like. Most of the time, when you do multi, you talk about the partial derivatives, df dx, df dy. You talk about coming in along those 2 nice paths. It is not enough for the 2 partial derivatives to exist to imply that the function is differentiable. The real generalization of what does it mean to be differentiable is, well, in one variable, differentiable really means the tangent line does a great job approximating your function locally. That's really what it means to be differentiable. In 2 dimensions, it's the tangent plane does a good job of approximating your functions. And you need to assume some kind of continuity among the partial derivatives to go from the partial derivatives exist and are continuous to the function is differentiable along any path. All right. The big result from multivariable calculus that we like is I'll call it just the Green's theorem. It's Stokes' theorem in a plane. How many of you remember Green's theorem? Huh. How many of you took 151 at Williams? Uh-huh. So when you take 151, you often talk about oriented paths. So I might give you some kind of contour like this. And I traverse the contour. And I want to calculate certain integrals along the contour. And so the integral, we'll call this curve gamma, along the closed curve gamma of p dx plus q dy is the double integral over the region. And I believe it's dq dx minus dp dy dx dy. So you convert a double integral to a line integral or a line integral to a double integral. And a lot of times you have these problems in multivariable calculus where you haven't learned Green's theorem yet. And the way the professors know that the answer they give you is correct is that they know Green's theorem, and so they can do the other calculation. So the way you prove this, or at least one way to prove this, is you chop your region up. And then are people feeling generous to me, or people feeling, let's make Professor Miller sweat?
Generous.
Thank you. That's the right answer. So I'm not going to worry about what's the most general curve we can do this for. We're going to do it for a class of curves that are called nice. It's a technical term. Right? So if I look at integrals like this, remember integration is oriented. If you go from left to right, that's positive area. If you go from right to left, it's negative area. So if I have a square like this, I always go counterclockwise. You always orient things counterclockwise so that as we walk, the region is to our left. Well, look at what happens over here. As I go through this region counterclockwise like this, and then go through the next one counterclockwise, I go through this segment two different ways. One's going up, one's going down. So if I break this integral over gamma into all these internal segments, all the internal pieces cancel. And essentially, you reduce what's going on to a rectilinear curve around it. I don't want to go into too much detail about what's going on really with the rectilinear curve. You know, if we have a curve like this, then it's clear that we can do it in terms of squares and rectangles. If I have something more general like this, well, what you would have then is you would have maybe something like this. And this rectangular part would be left over, and you would have to show that the integral over this top piece over here is extremely close to this, so close that even when you sum all the pieces, it's essentially the same. Okay. I don't really want to go through all those details, but you can make it rigorous. I'm just trying to give you a sense of what do you spend a semester on. So let's say we have this as our region, and I want to integrate p dx plus q dy. Well, when I look over here, is there any change in y? No. Is there any change in y up here? So there's going to be no contribution from the q dy from those two pieces. And over here, I will get contributions from the p dx. Okay? So let's look at the double integral of dq dx. So I have an integral of dq dx, and now I have to choose, do I want to do the x integration first or the y integration first? What are your thoughts? Do you want to find an antiderivative of dq dx with respect to x, or do you want to find an antiderivative of dq dx with respect to y? To x, right. Can you give me a function whose partial derivative with respect to x is the partial derivative of q with respect to x? Q, right? This is hopefully like your glaring arrows pointing, do me first. So because it's a nice rectangle, let's say this is the point AC and this is the point BD. We have x goes from A to D, and then y goes from C to D. And so when we integrate with respect to x, this is just the integral y goes from C to D, and we will have q at x d minus q at x c dy. And the reason is I can take any antiderivative I want. And so when I integrate it, I get q. I evaluate q first at d. Oh, wait a minute. I'm doing the integration with respect to x, right? Sorry. So it should be b comma y, and then minus a comma y. And now when you look at this, this is basically my q dy contribution. when y equals c, I'm getting the piece coming up like this, and when y equals d, I have the piece with the negative sign that's going in the opposite direction. Great. So this is just a quick sketch of why Green's theorem is true. I don't really want to go into too much detail. Is this enough of a sense to believe that I can replace these line integrals with these area integrals and vice versa? Okay. So now, let's talk a little bit about complex analysis. So we normally write I is or I am the square root of -1, so I squared is -1. So we write z as x plus iy with x and y real numbers. And it's amazing the power you get from adding the I. And we can ask, what does it mean for a function to be complex differentiable? Well, f prime of z should be the limit as h goes to 0 of f of z plus h minus f of z over h. And if you look at this, not surprisingly, this is the same definition we have in calculus. The question is, which functions will be differentiable? Somebody give me a good function to try. Simplest function to try.
Z itself?
Nope. That's the second simplest.
0, 1.
0, 1, any constant. Because if you choose any constant, then if you try z, you'll just get h minus, z plus h minus z is just h over h, which is just 1. So the next interesting one to try would be z squared. And then we would have the limit as h goes to 0 of z plus h squared minus z squared over h. This would be the limit as h goes to 0. The z squares will cancel. We'll get 2z h plus h squared over h. So we get the limit as h goes to 0 of 2z plus h, which is 2z. And what you can probably quickly realize from this point is that if I just give you z to the n, where n is any positive integer, it's the same as calc 1. Nothing new. We could try something a bit more interesting. We could try g of z is z bar is x minus iy. It's the complex conjugate. And it turns out this function is not differentiable. So if we try to look at now g prime of z, this is the limit as h goes to 0 of z plus h bar minus z bar over h. So this is the limit as h goes to 0 of h bar divided by h. And now the limit is going to depend on how we go to 0. We could take h to be maybe epsilon, with epsilon going to 0 and real. Or we could take h to be I epsilon going to 0 and real. And if we take h to be epsilon, then h bar is just h again and we get 1. But in this case, when it's I epsilon, the complex conjugate is going to be negative h, and then we get negative 1. So this would lead to plus 1, this would lead to minus 1. So there are some very nice simple functions that are not going to be complex differentiable. So for us, the functions we want to consider are the functions which are complex differentiable. Right. Any questions so far? So I've probably said this before, complex analysis is the very bad country club of mathematics. They only let certain functions in. Real analysis is the very democratic, oh, you want to be a function? Sure. You're welcome. Anybody remember a particularly nasty function from real analysis?
Well, there was like Cantor set and the function.
Okay, there was, but something that we've seen in this class.
Okay.
Oh, yeah. I forgot what it's called. It started like a D or something. Like the one that like goes to like, that had like 2 things in it.
That had what?
2 things.
It had a split definition.
Yeah.
Yes.
One of those.
But do you remember roughly what it looked like? This is,
e to the negative 1 over x, right?
yeah, g of z will be e to the negative 1 over z and then 0. Now this function is a perfectly acceptable real valued function if we force z to be real. It's in fact infinitely differentiable. Now, it's not a nice one if you take all of its derivatives at the origin is 0, which means its Taylor series is identically 0. And it should offend you for a function to have a Taylor series that converges but does not converge to the function. Right? That should not be allowed. And if you feel that way, then you should join the country club of mathematics and complex analysis, and you can look down and you can exclude functions like this, and you can say, I will not allow myself to study you. You are not welcome. In real analysis, you are a perfectly fine function. You don't have to agree with your Taylor series. The Taylor series can do its thing, you can do your thing. It's absolutely okay. What happens if we look at this as a complex valued function? So if z equals x, which is real, it's continuous, right? What if we let z equal iy, where y is real? Then we get e to the minus 1 over iy squared, which is e to the 1 over y squared, which goes to infinity as the absolute value of y goes to 0. This function isn't even continuous as a complex values. Not continuous in z. It's not even worth asking, is it differentiable as a complex valued function, because it isn't even it isn't even continuous. Now, just continuing how accepting real analysis is, you might have seen this function. F of x is x cubed sine 1 over x. So maybe they do x squared sine of 1 over x. This function is differentiable. And the only place where its definition is problematic is where? When x equals 0. But because I have an x cubed, this is always fluctuating between minus 1 and 1. It's fine. And when I go to the definition of the derivative, it's going to be, the limit will be fine, it will be 0. So it's going to be differentiable. It might even be twice differentiable. What's interesting is it's also 0 infinitely often as you approach x equals 0. 0 here, and you have infinitely many zeros coming in on both sides. And so we say that the set of zeros of this function has an accumulation point. That if you look at the limit of the set of zeros, it converges to a point and the function is 0 there. But this function is not identically 0. It turns out in complex analysis, if you have a function which is differentiable once, so here, I'll make a list of why complex is different than real. This should remind you of Chebyshev versus the central limit theorem, or Newton's method versus divide and conquer. When you assume more, what a shock, you actually get more back. Complex differentiability is a tremendous assumption. All those paths must give you the same answer. Real differentiability, boop, boop, that's it. 2 choices, big deal. So, 1, if differentiable once, differentiable infinitely often. All right, that's nice. 2, if differentiable, agree with Taylor series. So the Taylor series exists and it equals you. What else? If differentiable on all of C and bounded, then constant. So for instance, if you consider the Cauchy density 1 over 1 plus x squared, that's bounded, it's differentiable, but it's clearly not constant. A complex function that is differentiable and bounded has to be constant. This is actually one of the best proofs of the fundamental theorem of algebra, that a polynomial of degree n has n roots. And the last one I'll put down if 0 on a set of points that accumulates, then identically 0. And this is the last one that we're going to really need in the central limit theorem. So what this tells you is, imagine you have two functions f and g, and you want to prove that the two functions are the same. You can look at h of z is f of z minus g of z. And so if the two functions agree at a set of points, then that will be a set of points where h is 0. And so imagine I have two functions that agree at infinitely many points that accumulate. Then the functions must be the same. Yes?
So I'm a bit confused about number 3. So
Okay.
bounded as in like the result is within a
Well, no, if the original function is bounded, so there's some number, say 5, and that the absolute value of your function is always less than or equal to 5, then your function is differentiable, then your function is constant.
You can't have something that goes like
Nope.
from 3 to 5
Nope.
to 3 to 5.
Nope. As soon as you start saying you can't, the answer is nope. Again, exclusive country club. All of those things that you want to do, if you want to do them, go to real analysis. Real analysis will let you do them. This will not let you do it. It is extremely restrictive of which functions you study.
Is it because it has to be differentiable on all of C?
Yes, if it was not differentiable in all of C, if you're only working in strips, then you can do stuff like that, absolutely. But it's because it's on the entire plane. And so this last one here, what we would love to have is the resultant probability that if you agree with another function and have the same moments, then you're the same density. That's what we'd love to have. Unfortunately, it's that function g that we had earlier today that shows you, well, a real function may not agree with its Taylor series. Similarly, a sequence of moments may not uniquely determine a probability distribution. And there are probability distributions that have the same set of integer moments, but do not have the same density. Imagine, however, that rather than looking at integer moments, you looked at fractional moments. And imagine you have two densities that agree at a sequence of fractional moments that accumulate. Maybe they accumulate at the second moment or the third moment. Then that's enough to conclude that they must be the same density. And again, the goal is to try to give you a brief understanding of what is in complex analysis. If there's a huge desire for complex to be taught next year, please let me know, because right now the department is trying to decide on what classes to do, and we did teach complex this year. It's an absolutely wonderful subject. Okay. So what I want to do next is the Cauchy-Riemann equations. So when I teach complex, I have a battle between Cauchy and Riemann to see who is mentioned the most. You know, at the beginning of the semester, it's Cauchy, and you look like it's not even going to be close. But then Riemann starts to catch up, and by the end of the semester, it's close, very close. So I'm going to say f of z, I'm going to write it as u of xy plus I v of xy. And now, let's investigate what it means for our function to be differentiable. So, you know, f prime of z. This should exist no matter how I take the limit. So let's take the limit as h goes to 0 and it'll be real of u of x plus h y plus I v x plus h y minus f of x y. And this, I'm going to just abuse notation. Right? I should really write f of z. I can write f of x, y, I think you know what I mean. This is just saving my poor hand, which is hurt, from having to write the u and the v at just x and y. And then I divide by h. And well, when the dust settles, we'll have u of x plus hy minus u of xy. So we'll just get du dx plus I dv dx. Right? Any questions on this part? Then I could also do it another way. I could do the limit as h goes to 0 and it's real of u, oh, I should do this right, x y plus h plus I b x y plus h minus f of x y. And now, what should I divide by? Because really what I'm doing here is I have the point x plus I y plus h, or x plus I y plus I h. So what should I be dividing by?
Oh, that would be divided by I.
I have to divide by I h. Because that's really what I've changed things by. And so now when I do this, I'm going to get u x y plus h minus u x y over I h. I'm going to get a 1 over I du dy. Well, what's 1 over I? It's the same thing as negative I. If you multiply by negative I over negative I times I is negative I squared, which is 1. So this is the same as negative I. And then for the next one, I'm going to have I, the I cancels the I over there, and I'll have plus dv dy. So because these are the same, I get du dx has to be dv dy. And I have the i's, I get dv dx equals negative du dy. So these are the Cauchy-Riemann equations. Is it possible I've made an algebraic mistake? Come on, it's late in the semester. Of course it's possible. Is it even likely? Yeah, there's a good chance. So let's test it. What's the simplest function you can think of to test this on?
Well, I guess
F of z equals,
X, Y? Oh, no, that would be.
it's going to be a complex differentiable function. So I can't do z bar. That's not a complex differentiable. What's a complex differentiable function?
we know that a constant function, but maybe that's just
That's
too
just true
simple.
because then all the
Yeah,
derivatives will be 0.
They're all zeros.
So what's a complex differentiable function? You've got to be able to give me an example now.
F of z is just equal to x.
That's
Or
not
x.
complex differentiable. We did not prove
Oh, it's equal to z.
z would
Yeah,
work,
yeah.
or what else would work?
Z squared.
Z squared. So z might be too easy because if we chose z, then u is just x and v is just y. So du dx is going to be 1, but du dy would be 0. So if we chose the function f of z equals z, we might not be able to detect where the minus sign should be. So let's do f of z is z squared is x plus iy squared is going to be x squared minus y squared plus I times 2xy. So this is the first non-trivial example. And so again, this is another reason why I wanted to do this lecture, is it gives me an opportunity to talk to you about some great results. And just how do you think about things? How do you check your work? So du dx is going to just be 2x. Du dx is supposed to equal dv dy. dv dy equals 2x. All right, halfway there. Du dy is equal to minus 2y, and then dv dx is going to be 2y. And good, they do equal each other with a minus sign. This does not prove the Cauchy-Riemann equations are correct, but it does prove that they're at least consistent, and they at least match what we've seen. Now, if we go back a little bit and look at what's going on over here, I can write this as du dx minus dv dy equals 0, or maybe dv dy minus du dx equals 0. Does that remind you of anything? What did we start today with? Green's theorem. So essentially, you have a Green's theorem lurking here with the Cauchy-Riemann equations. So that if you just integrate f dz, it's the same as doing line integrals like this, which vanish. And this is why complex analysis has such wonderful integration results. It's extremely restrictive. But you're restricting yourself, if you remember multivariable calculus, to functions whose curl is 0. To functions where you have a conservative force. And so all of the line integrals become really nice. So let's do some integration. And so the goal is to show you how integration can be reduced to algebra. So let's integrate fn of z is e to the 2 pi I n z. Do you want to do it this way? No, I don't want to do it this way. Sorry. Let me do it this way. I'll do it as z to the n. And then what I'm going to do is I'm going to take a circle centered at the origin of radius r. So I can write z as r e to the I theta, or if you want, z is r cosine theta plus I r sine theta. And now, z to the n is r to the n e to the I n theta. Just raising it to the nth power. We've talked about this, I think, early in the semester. So this would just be r to the n cosine n theta plus I r to the n sine of n theta. And now let's integrate fn of z dz over the unit circle. Well, if I want the unit circle, the radius is fixed. It's just going to be r. And theta goes from 0 to 2 pi. So this is the integral. Theta goes from 0 to 2 pi. Fn of z is just going to be r to the n cosine n theta plus I sine n theta. And then what is dz? Well, r is fixed. So dz is going to be r times I times e to the I theta d theta. So it'll just be r I e to the I theta d theta. And we get this by just using the series expansion for e to the u and just differentiating term by term. So we're using dz is r I e to the I theta d theta. And now when you look at what's going on, I can pull out the r to the n, and I have an integral of cosine of n theta. Theta goes from 0 to 2 pi. What's the integral of cosine n theta or sine n theta over a complete number of periods? 0, unless what's true?
We're assuming n is an integer.
Yes.
It's a non-zero integer.
Right. So if n is if we have it as a 0, the integer 0, then we can get 0. Then we can get 1.
Yes.
Well, now actually, let's look at what we have. We have e to the I theta. Let's write this. Let's not expand it. Let's write this as e to the I n theta, and then we'll combine them. And so we'll get an r to the n plus 1. We'll get an I. We have an integral. Theta goes from 0 to 2 pi. We'll have an e to the I n plus 1 theta. So it'll be cosine n plus 1 theta plus I sine n plus 1 theta d theta. Right? And so the only time this integral is non-zero is if n equals -1. And when n equals -1, cosine of 0 is just 1, so we get 2 pi. Oh, and this is so lovely, isn't it? When n equals -1, what's the power of the radius? 0. So you just get 2 pi I if n equals -1 and 0 otherwise. So we can integrate z to the n over a unit circle centered at the origin. It turns out we can also handle this if we're integrating it at places other than the unit circle centered at the origin. All right, we still have 10 minutes. So again, normally this is done over an entire semester, but we're leading up to the big result. How many of you have never seen the green theorem or the Stokes theorem? Okay, how many of you have seen Green's theorem or Stokes theorem? Okay. So one of the big things you do with Green's theorem is I give you a region like this, and maybe the function blows up at this point. And you're like, oh crap, I can't use Green's theorem because it blows up. So what you do is you draw a small circle around this point, and you come down, go around the circle, and then come back out. And then you take the limit as that thickness goes to 0, and you shrink this down to 0 radius as well, and eventually you say the integral over the outside region is the same as just the integral over the circle. And that's the power, because in this region here, the function is differentiable. And you can use Green's theorem. So we can reduce integrating over regions that include points where the function blows up by drawing these little balls. And that's what we do in complex analysis. We reduce everything to, if it blows up, you draw a little ball around it, and you deal with that. How many of you have seen something like this with Green's theorem? Less. So this is one of the great examples of why we care about Green's theorem. And hopefully you can see that there is some kind of connection between complex analysis and Green's theorem. This is warp speed. You know, I just said, hey, look, if you've got the dv, du whatever, minus the whatever, doesn't that kind of look like Green's theorem? Yeah, kind of. Yeah. That's the level you should be getting at right now. This is the high level, 50-minute complex analysis video. But that should be enough to say, yeah, I can kind of see Green's theorem existing in complex analysis. It's not surprising. He gave me a heuristic. And then I can see, yeah, I see how we can use Green's theorem in regions like this to reduce integrating along a strange boundary to integrating along circles. And we can do the same thing with complex analysis. Now, what's nice is this is the 50-minute course. I don't have to worry about convergence. Screw convergence. So let's let f of z be the sum n goes from minus n to infinity of an z to the n. So here's a function, and I want to integrate over some curve f of z dz. What's the nicest curve to use? We don't have much time. Give me a nice curve.
Circle.
Circle. Such that at the origin. And so, not worrying at all about convergence or anything, this would be the sum, we would just interchange the sum and the integral. An, integral along the circle of z to the n dz. Ah, but we know what that integral is. What's the only little n that contributes? -1. And so it gives us 2 pi I times a -1. So we've converted integration to algebra, to finding the -1 Taylor coefficient. Now frequently, instead of doing the integral of a function, we do 1 over 2 pi I of the integral. Because if we do 1 over 2 pi I, then we don't have the 2 pi I factor over here. So the only piece that really contributes is the -1 piece. Okay. All that would happen is if I give you a more general function, what you would do is you would look at all the places where the function blows up. And you would play games like this, and you would reduce it to what happens at each of those points, and then you would sum the contribution of the -1 Taylor coefficient at the different expansions. I would expand the function here, I would expand the function here, I would expand the function there. And that's the beautiful theorem. So you would then get, more generally, it equals the sum k goes from 1 to, say, L of a -1 of f at the point zk. We will say these are the places where the function blows up. And so you can reduce the integration to something like that. Okay. So the only thing that's really left, we've got about 5 minutes, is somehow to argue that if you have a sequence of points where the functions agree, then the functions must be identically 0. So one of the big results is that if you're differentiable, you agree with your Taylor series expansion. So in complex analysis, we don't say differentiable. It doesn't sound snotty enough. This is, again, the subject of the exclusive country club. So instead of saying differentiable, we say holomorphic. It really means differentiable. It turns out that the big thing in complex analysis is holomorphic equals analytic. Analytic means you agree with your series expansion. Holomorphic means you are differentiable. And there's a beautiful theorem that basically says a function is determined by its values on a boundary. So a lot of times you might have some physics problems where they give you the boundary conditions and it uniquely determines what's going on inside. Complex analysis is ideally suited for something like this. And so we have f of z is like the integral 1 over 2 pi I f of zeta over z minus zeta dz. And this is like an integral over a circle with z inside the circle. So here's my circle. Here's some point z. I believe I've got this right. Or is it zeta minus c? I think it's zeta minus c. I apologize if I have things in the wrong order. Okay. Oh, and it can't be dz, it's d zeta. So this is a beautiful result. I'm not going to go through the full proof. If you assume that the function has a series expansion, it's not so bad. Let's just assume that this exists for now and play with it. If we take the derivative of this with respect to z, well, we've done differentiating identities all semester, and we've never worried about convergence before, so why should today be any different? And let's just pass the derivative with respect to z through the integration. Oh, now we just have a z minus zeta. We can take the derivative of that, no problem. Right? And you would just get z minus zeta squared. You have a -1, and then things go. What you would see is you keep doing this, you'll actually get values for all of its derivatives. And this is how you prove that the function is infinitely differentiable. If I now want to look at f prime of z, I would get like 1 over 2 pi I integral over gamma f of zeta over zeta minus z squared d zeta. And if I would take another derivative, I would get a -2 and -1, so that would cancel, and I would now get twice. And you'll then get 3 times, and you'll get factorials. You get like the nth derivative at z would be 1 over 2 pi I. I think it's n minus 1 factorial. It's getting late. It might be off by a little bit. F of zeta over zeta minus z d zeta. And so this gives you that all the derivatives exist. And then if you play games with the geometric series and expand things out, zeta is on the boundary, z is going to be of smaller absolute value. You can write zeta minus z as zeta 1 minus z over zeta. Z over zeta has absolute value less than 1. You could expand things out, and you can hopefully see, geometric series kicking in. So again, really fast blitzkrieg. So now the last thing to do is to just prove that if you agree at a sequence of points that accumulate, then you must be identically 0. So if accumulate, then 0. So imagine we know f of z has a Taylor series expansion. And let's do the expansion about the point where it accumulates. So accumulate, we might as well assume that it's accumulating at the point 0, make life easy on ourselves. So if it accumulates at 0, it has a Taylor series expansion. If the Taylor series expansion is all zeros, we win. So let's assume it's not all zeros. There must be a first coefficient that's not 0. So it'd be, an z to the n plus an plus 1, z to the n plus 1. Doesn't this remind you of how we did the central limit theorem? So let's just write this as an z to the n 1 plus crap of z. And what must be true about crap as z goes to 0? It converges to 0. So this has to go to 0 as z goes to 0. But if we stay away from 0, this is not 0. And this contradicts that we were supposed to have a sequence of points accumulating where the function was 0. So here's z equals 0. We're supposed to have a sequence of points accumulating, getting closer and closer to it, where the function is identically 0, where the function vanishes. But we've just shown that this can't be 0 once z is sufficiently small, because crap will be less than 1 in absolute value, and it can't make this equal to 0. So what do we use? We use that because the function was differentiable once, it's infinitely differentiable, and it agrees with its series expansion. And then because it agrees with its series expansion, we then know that if it accumulates, it has to be identically 0. Now if you look at the appendix in the book on complex analysis, this is the key result. That if we want to show that things with the moment generating functions work, if the moments are the same along a string of moments that accumulate, then the functions must be identical. And this is essentially what we need to make probability rigorous. And it is a completely different subject than real analysis. Now, it has a lot of components from real analysis. I refuse to teach complex analysis at the school without having real analysis as a prerequisite. There are times when they ask you, are you willing to do something for the good of the department? And most times, of course. But there are a few times that, no, it's not for the good of the department. You may think it's for the good of the department, but complex analysis should not be taught without real analysis as a prereq. You have so many convergence arguments going on, so many limit arguments going on. You want to be familiar with the language of real analysis. But once you have that language, the implications and the applications are profoundly different than what you would see in real analysis. This is absurd. A function that's differentiable once is infinitely differentiable. We don't have that in real. If you're differentiable and bounded, you're constant. We don't have that in real. Think of sine and cosine. These are wonderful functions. But the strange counterexample that killed us in real analysis is not even continuous in complex analysis. It is such a restriction to say that a function is complex differentiable. It's not surprising you get a whole lot more. And the last point to just emphasize again is you always want to say to somebody, where is the miracle? Why does everything work out? When we did the German tank problem, we had this beautiful Pascal triangle identity, that this diagonal sum had a closed form expression. What's the miracle here? Green's theorem. We're talking about functions where Green's theorem applies. All right. So what I will do